In this video, we're going to be looking at a table found in the Historic Building Code as well as the California Existing Building Code to see if we can use that information to save money on a seismic retrofit. This table refers to two building materials that are no longer used. These are called archaic building materials. And the first one is lath and plaster over wood. Lath and plaster over wood is the same as a plaster wall when you're in a house. So if you go into a house about 1942 and you can even just knock on the wood with your fist, and it'll just, on the walls with your fist, and it'll just feel real hard, very, very different than what it feels like with sheetrock. And what that looks like is this right here. It's a regular wall. It looks just like sheetrock, but it's put over this wood lath right here. So contractors came in, they put all these narrow slats of lath on it, and then they put the wet plaster over it. If you were going to go on the other side of that wall, it would look like something like this. So there's the wood lath right here that's going like that. And then you can see how the plaster has oozed through the cracks in order to bind itself to the lath. A plaster that's put over metal lath, that's the same as plaster put over chicken wire material that you see on the outside of the house. The common name for that is stucco. Before gypsum was used exclusively in homes, we also see it as a lath over which plaster was put. This is, 38 to 41, something like that. We don't see it very often, and we call it button board. And let me show you what it looks like. So here is basically it's the same as sheetrock or drywall, and they put holes in it. So you can see all these different holes. And then they would put plaster on top of that, and you see where the plaster is oozing through like that. That's doing the exact same thing that the wood used to do, but this is obviously much cheaper for a contractor to do than that very labor-intensive wood lath. This table is from the 2019 California Existing Building Code, and it tells us that plaster on wood or metal lath can resist 600 pounds per foot for seismic shear. And for plaster on gypsum lath, it can resist 550 pounds per foot for seismic shear. I'd like for you to notice that this here is the strength values. Now strength values, those are the actual tested values. So for example, they would have a wall that's made out of plaster on wood lath. Then they would apply a lateral force to it, and they would find out that at 600 pounds per foot of lateral force that the specimen would fail. This is the same table from the 1997 Uniform Code for Building Conservation, and these values are quite a bit different. Here it says that for plaster on wood or metal lath, it has a value of 200 pounds per foot for seismic shear, and for plaster on gypsum lath, it's 175 pounds per foot for seismic shear. Now notice up here where these are allowable values and not strength values like we saw before. Now an allowable value is a value that's given when the designer thinks, well, the contractor might have screwed it up, the materials may have been bad, if there was a building inspector maybe didn't look at things carefully. So you just assume the worst. And even if you assume the worst, if you use these values here, the wall should perform as listed here in this table. So let's see how we apply the information in this table to an actual house. So here's a sample 1,000 square foot house. It's 25 by 40, and it's plaster on the inside, it's stucco on the outside. It's what's considered a heavy house at 50 pounds per square foot. And we determined that it must resist 5,000 pounds on each side. So over on this side here where it's 40 feet long, there is plaster on the inside and there is stucco on the outside. So here we have 40 times 200. Remember, we're using the allowable value, and that gives us 8,000 pounds resistance on the outside, 8,000 pounds of resistance on the inside because plaster and stucco have the same value. So we end up with 16,000 pounds of resistance as is. And if we only need 5,000 pounds, there's really no point in doing any work here. There's absolutely no point at all. Now, some people might be concerned, well, how well is the floor connected? And here we go back to Appendix Chapter A3 of the California Existing Building Code, and what it tells us there is that connection you just don't need to worry about it. It does not need to be verified. So there's no extra metal, no connect that needs to be made there. And it's our experience that the mud sill, you'll find a nice big, a 20 penny nail about every 2 feet, 2 to 3 feet along the whole wall. And that's, probably sufficient. But if you want to go ahead and augment it with some URFPs on the outside, you could go ahead and do that. Anyway, you'll have a really strong wall without doing anything, and you don't compromise the the fire safety. You don't they have to paint it. It's really expensive to do seismic retrofit work, and this will save a lot of money by using this table which we've just researched. Now there's one part of this table we don't use very much, and that's the part that has to do with horizontal diaphragms. A horizontal diaphragm is either a floor or a roof, and because those things don't fail in earthquakes, we don't look at that part of the code, except in one case. Now there's a part that says floors with straight tongue and groove sheathing, 100 pounds a foot in seismic shear, and let me explain what that is. A horizontal diaphragm with straight sheathing would be one like this, and it has boards that just run straight across. So they're just boards that run like this, and they don't have any angle or anything. Now if you take that and you move it up like this is basically the same thing as a wall. So that would be a wall with straight sheathing. So this is the same as this house right here. So you see how there's boards that run like this? Those are actually tongue and groove boards, so that means they sort of interlock together. And then you can see the siding comes this way and the siding comes this way in a horizontal fashion. Same thing over here. It's in a horizontal fashion. And you can barely see this house over here, exact same, boards in a horizontal fashion. And these boards are actually the weakest sort of siding you can possibly have. So that's 100 pounds per linear foot. Now compare that to stucco, which is 200 pounds per linear foot. So stucco is actually twice as strong as is than wood. This is also borne by empirical evidence. When I was doing research on cripple wall collapses, I looked at about 53 photographs, everything I could find on the internet, and out of those 53, only 2 of them involved cripple walls with stucco siding. So this is further evidence, besides this code, that stucco is much stronger than wood siding. Big deal. Why does this matter? Well, as we just saw, there was a wall that needed to resist 5,000 pounds of lateral force. And just looking at the existing stucco and the plaster inside, it could resist 16,000 pounds of force as is. So there was absolutely no reason to waste the client's money retrofitting that wall when it was already fine.